For the second half, we kind of go into random variables and binomial and geometric distributions. A random variable basically is kind of what we've been doing, just a little more formalized. When I go in and I am describing the outcomes of some chance process, I'm dealing with a random variable. So when and we're going to do an example we've used before, when we were trying to see what are the outcomes of flipping 3 coins, we listed the entire sample space. That is a random event. Going in, and then we turn that random event into a random variable by giving it some numerical meaning. Random variables involve the same probability rules, so it cannot be bigger than 1. It cannot be less than 0. If I add all of them up, it has to total to 1. Everything that we did in the first half of Unit 4, all of those rules still kind of apply. With the example that we're going to kind of go through today, it's going to be a very basic one. However, it's going to kind of carry over into all of the things that we do in the future. So the first thing that we kind of look at, it says, suppose we toss a coin 3 times. So a coin has 2 sides, heads, tails, typically. And so if I wanted to see the total number of outcomes, this would be my first coin, 2. And then I would multiply it by my second, multiply it by my third, and in total, I should have 8 possible outcomes. This is something that we've dealt with before. So that means the probability of any one outcome is going to be 1 out of 8. Now, when I go in and start listing out the sample space, we've done this before, and I usually kind of start with the scenarios where it's just one side only. So heads, 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 and tails, tails, tails. And then I start to change one at a time. So I will maybe do tails, heads, 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 tails, heads, 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 tails. And then I do the same thing for the other side. Heads, tails, 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 heads, tails, 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 heads. Now, if you have the time and if it's beneficial to you and it's not something that's got a lot of different combinations, sometimes it's helpful to just list out the sample space and kind of see what you're dealing with. Now, the sample space isn't always just here's all of the possible outcomes that I could have. Sometimes you're doing things like the multiplication rule. Like, what if I pick one person that got the answer wrong and then pick one person that got the answer right? That would be the multiplication rule of the probability they got it wrong times the probability they got it right. So a lot of these kind of mix in some of those probability questions we had from 4.1 to 4.4. So once I have my sample space kind of built out, we can go in and fill in our table. Now we're going to formalize this in just a second, but typically for random variables, you define it with a capital letter. X is the most common one, but you could really choose anything that you want. I usually use XYZ. And then you define what you are actually looking for. So in this case, we are looking at the number of heads out of 3 coin tosses. Now, what this is doing is it's taking categorical data. So in our case, for very beginning of the year, we talked about categorical versus quantitative. If I'm doing heads, tails, that is categorical. It's either going to go in the heads group or it's going to go in the tails group. But by changing this to the number of heads out of 3 coin tosses, that's giving me something to count, and that's turning it into quantitative. If you are doing anything with random variables, it has to be some measure of quantitative data. Otherwise, nothing that we do in terms of finding the mean and the standard deviation and all of that stuff is really going to matter. So in our case, we have, what are these individual probabilities? So we have getting 0 out of 3 tosses where you have a heads, 1, 2, and 3. I'm going to go for the obvious ones first. X equals 0, getting no heads at all is when I have my tails, 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 which would be 1 out of 8. And then the next obvious one is getting 3 heads out of 3 tosses, which is going to be the heads, heads, heads. And so that's going to be another 1 out of 8. And then in order to find the others, I just look at my sample space and I see which one of those outcomes satisfy what I'm looking for. So the first thing that I have is, what is the probability of getting one head out of 3 tosses? So this is one head, one head, one head, which is going to be 3 out of 8. And then I'm going to do the same thing for my 2 heads out of 3 tosses. So that's 2 heads, 2, and 2. So 3 out of 8. Now, just a little kind of hint and what I will sometimes do if I know, maybe by the time you get to the last outcome, I know it's not true for this question, but maybe by the time you get there, it's like I'm going to have to multiply a lot of things. I'm going to have to make sure that I have everything kind of accounted for. Sometimes that's not always like the most fun. So what I will do if I know I have the first 3 correct, I will sometimes just be like, okay, well, I know this entire sample space has to total to 1. So if I know that, and I know that I know 3 of the probabilities, I'll just do 1 minus the ones that I do know. So 1 over 8, 3 over 8, 3 over 8, and I'll just take a complement. And there have been questions on the AP exam in the multiple choice section and sometimes in the FRQ where they'll give you a table and it'll have 4 out of the 5 values there, and it'll say, what is the missing probability? And it's not something where they want you to like think of, okay, do I need the multiplication rule or do I need to do something and build a tree diagram? No, you just take the other probabilities, you add them together, you subtract it from 1. That should hopefully be a very, very easy question. Because again, the entire sample space probability has to be 1. And so now that we know what our probabilities are, the easiest but often missed question on FRQs, because you will be guaranteed to have one FRQ related to probability, for sure. Now there's a couple of ways it could go. It's probably going to be more of what the second half of Unit 4 is. The first half leans better to multiple choice. But you will have one probability FRQ, for sure, guaranteed. They basically listed online that that's one that you will have. Now, for the most common question that gets missed, that shouldn't get missed, is they will sometimes ask you to create what we call a probability distribution. And a lot of people, because there's going to be a lot of information that goes into your brains between now and May, whatever, they see that and they're like, oh my God, what am I supposed to do? Like, am I supposed to draw like a curve? Am I supposed to do like, what am I doing? If they ask you to create, and I'm just going to kind of give you some keywords, probability distribution for whatever, all you need to think is that I need to make a table. This is, as a stats teacher, one of the more like, oh, they should have got that right. Because it's not hard. They literally want you to have a table where you list the outcomes and you list the probabilities. And sometimes it's as simple as just reading the question and seeing what they're telling you is going to happen. So it's a problem that you shouldn't miss. So in this case, I'm going to kind of show you the table first. These are going to be my outcomes. And these are going to be their probabilities. So in our case, we've calculated all of this. 1 out of 8, 3 out of 8, 3 out of 8, 1 out of 8. And doing just that alone gives you, usually if it's like an A, B, C, D question, it gives you a 1 out of 4 on the FRQ. Just taking the information you have and organizing it appropriately. Now, again, sometimes the probabilities themselves can be a little challenging, but most people, if we go in after the fact and talk about FRQs and I say, well, you should have just made a table, they're like, oh, that's what I should have done. So don't overthink that question. It's literally organize your information. Now, if I wanted to kind of go a little in a different direction, they technically would also take a histogram. I don't think they're as useful to you just because then you have to kind of scale it and you have to make it and then you have to be able to read it after the fact. Histograms, remember, they go up until the value on the x-axis scale. So when I look at my first bin, my first class, it looks like it's 0 to 1. The 1 is not included, which is why it only has a height of 1/8. And then the 1 to 2, the 2 is not included. The 2 to 3, the 3 is not included. The 3 to 4, the 4 is not included. So everything in a histogram is up until the next scale marker. Just to kind of loop in some language, this is a normal distribution. That means it is unimodal and it is symmetric. That is not always true for every probability. Sometimes your chance of something happening decreases as you kind of continue on. Sometimes it increases, but it all kind of just depends on the situation. So this is a probability distribution. Don't overthink it. It is literally just make a table. Organize your outcomes, organize your probabilities. Now, to kind of formalize the requirements that you have to have for a probability distribution. Every probability distribution must satisfy 3 things. There is a numerical, not categorical probability or random variable x. Let's fill that in. Random. Typically, it is x, again, just because x doesn't get confused with other numbers. Like some people, if you pick s, sometimes it looks like 5. Pick I, sometimes it looks like a 1. And each of the values of x has an associated probability with it, the sum of all of the probabilities in the distribution. If I was taking the sum of all of the probabilities, it must equal to 1. Language, this is always going to be sum, add everything together. And all of the probabilities must be between 0 and 1. One thing to remember too, you can have 0 and 1 inclusive, meaning you can have a 0% chance of something happening. You can have a 100% chance of something happening. You just can't have a negative chance or a 110% chance, 0 to 1. Now, in these questions, a lot of what you'll find is they're going to ask you things in terms of less than, greater than, equal to, versus like, I need this specific combination of events, which is how it kind of differs from the first half. Now, in our example, our 3 coins, we have our probability distribution. Again, remember, probability distribution is just the table. Bless you. So they ask you a couple of things about this. So the most common one is we just want you to find one individual probability. And in this case, they want us to find when is x equal to 2. And so that is when the random variable equals 2. And that means all I have to do is go to my table, go to the number 2, and then see the probability that's associated with it. In this case, that is 3/8. Which is 0.375. Now, the next one, also another not crazy hard. Greater than or equal to 2 means we want something where it's 2 or more. And that is something with these questions that a lot of people kind of get confused on. They don't always use the exact same language, so you kind of have to decipher what they're looking for. So 2 or more would mean that I'm including not only 2, but I'm also going to include 3. So when I calculate this probability, I'm going to take 3/8, wrong number, 3/8, 1/8. I'm going to get 4/8, which is just 0.5. And the one that I find to be the most commonly missed one is the ones where it doesn't have the equal to sign. Because a lot of people mix up, should I be including this value? Should I not include this value? Am I going up until this, down, whatever? Something about it gets to be confusing. So I want everything less than 1. So in this case, that means I'm not including 1. And so the only thing that's less than 1 is 0. So this is going to be 1 over 8, which is 0.125. And this alternatively could have also been asked as x is equal to 0. You could have also even said x is less than or equal to 0, and it still would be the same thing. But you kind of have to pay attention to if it's equal to, if it's not, what numbers are below, what numbers are above. I will say this, it's not always in like numerical order. Like it's not always 0, 1, 2, 3. Sometimes you have things like they made a profit of $50 and they lost $100. So my outcomes would be 50 and negative 100. So it kind of depends on the question. Don't always think it has to be going in numerical order. It really just depends on what they're asking you. So common questions they could ask. And then we're going to kind of go in and talk about the differences between discrete and continuous. Continuous, for the most part, we're not really going to cover today. We get more into things like that in the next kind of lessons, mostly into going into hypothesis testing, which we'll barely touch it today, but we're not going to go too far. Discrete random variable is kind of where we're living right now. A discrete random variable takes on, and the big definition of discrete that we had at the very beginning of the year, it's a fixed set of possible values with whole number outcomes. Think about the questions where I asked you, how many siblings do you have? How many AP classes are you taking? How many pets do you have versus what is your height? What is your weight? How fast can you run 40 yards? Things like that are continuous, where you can kind of measure in between two values. Discrete is going to be like you have the two values. So random variables are usually capital letters. Again, we talked X, Y, Z, most common ones. Random variables can be discrete or continuous. And random variables must be numeric in value, meaning categorical data must be described numerically. Now, that doesn't mean you can't use categorical data. That's what I just did. I went in and I took the number of heads from a categorical event. Now, the mean of a discrete random variable is the mean outcome for infinitely many trials. Infinitely many. Now, if I kind of relate this to what we did in the first half, this is what we would call long run behavior. Think of our coin example. If I flip a coin 10 times, I'm not guaranteed to get 50-50. But if I flip it 10,000 times, that probability is going to get closer and closer to 50% heads and 50% tails. That is long run behavior. Short run behavior is completely unpredictable. Like you don't know what's going to happen if you only do things a couple times. You could get all 10 of them are heads, or you can get 0 of them. But over time, you should get close to those theoretical probabilities. Now, we think of these expected values as the average. So one thing that I try to really convey, because a lot of people get them confused, not confused, but they don't know that they mean the same thing. If you ever read a question and they say, how much money would you expect to make by playing this game? I'm thinking of all of the questions I got from Math Lab yesterday. If they ask you expect, all they want to know is what is the average. And so anytime you see that, don't overthink it. Don't be like, am I supposed to like guess? Like, what am I doing? You're literally finding the average. And so we define the average as mu of x. And if you forgot that this symbol is mu, it is. And then it also can be written as the expected value of x. College Board will use these interchangeably. So sometimes they'll give you mu of x, sometimes they'll say e of x. They literally mean the same thing. They mean you are finding an average. And so the way that we do this is we are going to go in and we're going to take every single outcome and it's going to get multiplied by its probability. And you're going to go in and you're going to find the sum of all of those outcomes times their probability. I'm going to give you a really generic kind of formula, the one that you'll actually see on your formula chart. I'm going to use x1, p1, x2, p2. You keep going until you get to your last outcome, xn, pn. So the first line that you see is not the one that's on the formula chart, but it is kind of showing you what it's doing. x1 times p1, x2 times p2, xn times pn, and then we go in and we add them all together. Now, what you'll actually see on the formula chart from College Board is they will give you the sum of xi times pi. So this one is on the formula chart. If it is on the formula chart, it will be on your test, so you don't have to memorize it. We will kind of talk calculator in a little bit to see that there are ways your calculator can help you for this. But I truthfully think that this is one of those problems where sometimes I just take the average by hand. Like, I don't always go to the calculator if the only thing they want me to find is expected value, because it's as simple as multiplying, adding, multiplying, adding, multiplying, adding. And that's not too bad. So again, that is on your formula chart. The top line is not, but the one that is in black is. So you don't have to memorize that. Now let's go ahead and let's try one of these out. Northwestern University posts the grade distribution for its courses online. Students in Stats 101, they got a distribution of grades from A to F. And the first question that I'm seeing is create a probability distribution. Yes, I know, it kind of sounds weird. It's like, what do you mean? All they want, again, is a table organizing your outcomes and your probabilities. And they even define X for us, which is it represents the student's grade on a 4-point scale with A equal 4. Sometimes they don't define it for you and you have to define it, but they told us they want it to be X. So I'm going to go in X, probability of X. And if it's on a 4-point scale, we have A, B, C, D, and F. Let's go. And then all I have to do for this probability distribution table is fill in the probabilities. So that's going to be 0.26, 0.42, 0.20, 0.10, and 0.02. And that would literally be it. We've seen many FRQs where the first question of the now they may make you do a little work for the probability, but this has been part A. And if you can get this done on that FRQ, you already have a 1 out of a 4, because that's what they grade you on, 0 to 4. Now that I have my probability distribution, I can use it to answer my other questions. The one thing I'm going to point out first, because I don't want you to forget to do this, is if they have the word interpret, you have to write a sentence explaining what your value means. I give you kind of a sentence stem in your notes. If this were a test question, you would not have a sentence stem. So find and interpret the probability that X is greater than or equal to 3 if X represents a randomly selected Stats 101 student. So I'm going to have the probability X is greater than or equal to 3. Now, what that means is I'm going to be looking at the probability that X is equal to 3 and the probability that X is equal to 4. I guess or is the better word, or the probability that X is equal to 4. I always get the question, what do I actually have to write on my paper? I would need, again, the same thing from the first half, a probability statement. There we go, bam, probability X is greater than or equal to 4. I would need your work, so that doesn't necessarily mean I need what's in black, but I need you to tell me I'm taking 0.42 and I'm adding it to 0.26. And that is what's going to give me 0.68. So the three things that I need are still consistently the same: a probability statement, either your fraction setup, or in this case, we're adding decimals, your work for your answer, and then your final answer in decimal form. So now that I know it's 0.68, I'm going to jump to writing out my interpretation. The probability that a randomly selected Stats 101 student, and I'm going to be specific, at Northwestern University, gets a, and in this case, we're going in and we're looking at the context of the question. I'm not necessarily saying this is them getting a 3 or higher. This 3 relates to them scoring a B. So I'm going to say a B or better. You can say higher in that case, but I don't want to, if I'm asked to interpret, they want you to put it into the context of the question. So in this case, it's a B, is approximately 68%. Now, in the next kind of interpretation we're going to do, you'll see that I take the numbers and relate it to the letters. You can also do that, but give it some meaning, especially in those cases where you're taking categorical data and turning it numerical. If it was money and I saw that like they make $15, I would just say they get $15. Like you don't have to convert it to anything. But in the case of changing things around, make sure you show what that actually means. Now, write the event. The student got a grade worse than C. So that would mean they got a D or they got an F in terms of values of the random variable X. What is the probability of this event? So the one thing to remember is a C is represented by a 2. And so I want everything less than 2. So I can say that by doing the probability X is less than 2. I can also say that by doing the probability that X is less than or equal to 1. And both of those statements mean the exact same thing. They mean I'm going to look at the probability of 1 and I'm going to look at the probability of 0. I don't care which one you write. Then we go in, and again, you don't have to write this part, but I'm going to take the probability that X is equal to 0, and I'm going to add it to the probability that X is equal to 1. What I like to see is your actual calculation. So 0.02 plus 0.10 is equal to 0.12. Now, this question did not ask me to interpret, so I don't have to write a sentence. If you do not see the words interpret, you don't have to write one. If you want to, you can. College Board has a really weird rule where if you write something and it's wrong, even if it wasn't a part of the question, they technically have to kind of dock you for it because you're not interpreting things correctly. So if they don't say it, I wouldn't write it, just in case something you say is not correct. Now the last little piece. Compute the mean of the random variable X. Interpret this value in context. So remember, mean, also referred to as expected value, is the summation of xi times pi. This formula you don't have to remember. It is on your formula chart. But one of them that I think not too bad to do by hand. So I'm going to go ahead and do mu of x. And what you're doing is outcome times probability. So I have 4 times 0.26. I have 3 times 0.42. I have 2 times 0.20. I have 1 times 0.10. And I have 0 times 0.02. Plug all of that into my calculator, and I get 2.8 as my letter grade. Anything in terms of mean and standard deviation has to have a unit. And usually for questions where you go on to interpret in context, they're not too nitpicky about having a unit in the calculation, but when you get to the interpretation, it would have to be there for sure. Again, not super hard. Most of the time, I just do this by hand versus going to my table and plugging it into my table, running the calculator, seeing what it gets, whereas I could just type in numbers and get my answer pretty fast. In the case of our mean, it's always going to be under the assumption, kind of how we defined it, if we were to select many, if we were to do this again and again, you have to have something stating that this is not just a short run event. This is long run behavior. If we were to select many Stats 101 students at Northwestern University, we would expect an average of 2.8 letter grade. I guess we'll go there, which is between a B and a C. So since we're kind of in the middle, closer to a B, but between a B and a C. So make sure you have some type of statement including that this is happening again and again and again. Now, the last thing we're going to talk about today is standard deviation. Standard deviation is typically one of those where I say the calculator is usually better. For doing it in terms of a random variable, it's not the worst thing. We're actually going to do it by hand because I kind of want to make a note about questioning for that. However, just to kind of go through things, one little basic reminder. Whenever you're going in and you are finding a standard deviation, it is always going to represent the typical distance from the mean. So again, if you see expected value, you should also be thinking that that means the mean. But basically, how far off are we? If we take it back to normal distributions, most of our data points are within 3 standard deviations of the mean. And so I have my generic example, x1, p1, x2, p2, xn, pn. Whenever we first introduced standard deviation, we talked about how standard deviation is taking something called the variance and taking it and finding the square root of the variance. So if you get questions that ask you about variance, it's literally going to be kind of the stepping stone to a standard deviation. Variance measures how far off our values actually are from the mean. So the general outline of this formula is going to be, you're going to take your outcome, you're going to subtract your mean. I know I accidentally put dots here and I only noticed it right now. These should be subtractions. I'll take it. Which after 3 classes, I probably should have noticed it earlier. Okay, thank you. Outcome minus the mean squared times the probability. So basically, this is what you're doing for every single outcome that you have. Sometimes your table is only 2 outcomes. Sometimes it's 5, sometimes it's 3. But this is what the number of terms you would have depend on the number of outcomes. So the variance itself, you'll notice, is sigma squared. And when I go in to find the variance, that is going to be the summation of xi minus mu of x squared times pi. Now, that is not the formula they give you on the formula chart. They give you only the standard deviation formula. So that means I'm taking what I just wrote and I just have it within a square root. Xi minus mu of x squared times pi. This is the one that is on the formula chart. And yes, please change those multiplications to minuses. That's what I get for copy pasting. So we're going to do this by hand, and I'm going to kind of explain why we're doing this one by hand. And usually you hear me say like standard deviation in your calculator every single time. We're starting to enter into the territory where College Board, they know that most people, at least who teach stats now, they're moving more in the direction of using the calculator. There are a lot of like older methods for finding normal CDF and for finding inverse norm. They have like a bunch of tables you can look at and you can match up the numbers, and that's my z-score and this is my p-value. There's a bunch of different things you could do. But most people these days have moved to teaching it in the calculator, and eventually we'll get to a point where everyone's teaching it in Desmos. But they still want you to know how to use the formulas. So what they do now is they know you're going to use your calculator. They know you're going to plug it in, you're going to find it. But what they do is they will go in and they will ask you multiple choice questions, and those questions will be, which of these formulas correctly finds the standard deviation? And so they'll give you 5 answer choices that look all almost correct, but like the numbers will be switched up, the signs will be changed, maybe it wouldn't be squared, and you have to identify which one would correctly calculate the standard deviation. And so we've been seeing that kind of pop up a lot more as people move towards doing things in the calculator. So for the Northwestern example, we're going to find and we are going to interpret, because they want us to write a sentence explaining the standard deviation of the grade probability distribution. So the first thing I'm going to do is I'm going to find this by hand. Now, I'm not going to make you actually plug it in your calculator, but we're going to write the formula out. It's very long, truthfully. So I'm going to give you a really long square root. I also write big. If you write small, we don't need one as big as I have. Once I have my square root, remember, this term is kind of happening for every single outcome. So I'm going to go in, I'm going to take 4, because that's my first outcome, minus 2.8 squared times 0.26. And it's literally just plugging in numbers. Yes, it is kind of annoying, which is why I usually say use the calculator. But I want you to at least be prepared in the case that they ask you which of these calculates the standard deviation correctly. And then I have 3 minus 2.8 squared times 0.42 plus 2 minus 2.8 squared times 0.20. And I'm just going down the list of my table. 1 minus 2.8 squared times 0.10 and 0 minus 2.8 squared times 0.02. And so just to kind of give you like maybe they would write this. My other answer choices could potentially be it doesn't have the square root. It could also be it doesn't have the squared. It could be that they're adding the numbers instead of subtracting. It could be that they're subtracting the numbers instead of adding. So it could have just a bunch of different options where they're just testing, like, do you even know what these formulas are? And a lot of people get confused on them. I will say the ones that we've seen pop up, it's never been a formula that you didn't have on your formula chart. And so, or a formula that you should know, and I've told you you had to memorize and you had to know it. It's never been anything like just out of left field. So in this case, after all of that and all is said and done, it's 1. 1 letter grade. That is the standard deviation. Now, I know it seems kind of crazy. Like, that's a lot of numbers. How did it end up being 1? Think about your outcomes. My outcomes are 0 to 3. How big could my standard deviation really be if my outcomes are 0 to 3 and my average is 2.8? I can't have a standard deviation of 15 because I'm not going to have grades that are 15 less and 15 more than 2.8. So 1 makes sense with what I have. So to interpret, again, you'll notice I have, if we were to select many Stats 101 students, again, long run behavior. If we were to select many Stats 101 students at Northwestern University, we would expect the typical deviation from the mean of, I always like to kind of plug in the mean value into my interpretation because that is really the deciding factor for what your standard deviation ends up being, to be about 1 letter grade. Don't forget to include units for any interpretation sentence that you are writing, other than if you're finding a probability, that's just a percentage. Okay, Now, the last little bit we're going to kind of fly through because we don't really cover it today, but I do want to at least talk about the continuous random variable. Continuous random variable takes on all possible values in an interval of numbers. The probability distribution of X is described by a density curve. So I want you to think kind of like our normal distribution where we didn't necessarily have specific values that we were finding. We were doing things like, what's the probability it's less than this or greater than this or in between these two things. That was a density curve where we were finding individual probabilities. And the density curve always equals to 1, which again makes sense because all of the probabilities we found were decimals. And the probability is on the y-axis in the distribution, so finding the area equates to finding the probability, I'm just going to abbreviate because my space is too small, of getting an interval of numbers. Again, we never in our normal CDF inverse norm business ever found exact values. We always did less than, greater than, or between. Now, the probability at an event, for example, if I was just doing equals to 2, is 0 for a continuous random variable because the area under a point is 0. Again, which is why we never did normal CDF equal to 5 or anything like that. It was 5 or less, 5 or more, between 5 and 10. Now, the mean and standard deviation of a continuous random variable are found using integration. Again, not something we're going to do. That's more calculus side of things. Everything that we need for continuous data, our calculator gives to us in those calculator functions. So we don't really worry about it. We're like, the calculator's going to do it. I don't have to do it. Not going to make a big deal out of it. Now, the reason why we go in and we do these random variables is so that we can go in and see, as we progress on, if I'm testing people's claims, I need to see how likely is it that these things are going to happen so that I can either agree with them or I can disagree with them. So we're collecting evidence, we're using simulations, we're running probabilities to see if what they're saying is true, if what they're saying is what I'm seeing. Now, the very last thing we're going to talk about is the calculator, because the calculator is also still an option. You get a calculator on your entire AP Stats exam. You get a calculator on this test. So I want you to take out your calculator and I want you to go to your lists and I want you to go to Stat, Edit, and in List 1, we're going to have all of our outcomes from our table. And in List 2, we're going to have all of the probabilities. And you may have already had this in your calculator if someone didn't do anything past the notes, or it may be completely different numbers from the math labs. So we have List 1, List 2. And this works in any situation where you have a probability distribution table. I will then go in. A lot of people will say, is this 2 variable stats now that I have 2 columns? Technically, we still only have 1 random variable. The random variable is L1, and the probability with which it occurs is L2. So I'm going to go to Stat, I'm going to go to Calc, and I'm still going to stay in one-var stats. Now here's my little disclaimer. You may already have it say L2, so second number 2 for frequency list. I reset the calculators between tests. So when I reset the calculators, the frequency list is going to be blank. So make sure that you know when I go to run this data, the frequency list needs to say L2. It needs to have the probabilities as the frequencies. Otherwise, you're going to run it and it's going to give you the information for L1 only, and it's not going to be correct. So L1, L2, and then you hit enter. And there's 2 kind of things that are important. The X bar is going to represent the mean, and there's a note about it in that little box you have on your paper. And the sigma X is going to represent the standard deviation. So notice I have 2.8 and I have 1, which is what I got when I did it by hand. There are other things in here that are useful. They'll tell you the 5-number summary, the min, Q1, median, max. But for the most part, you get more questions on what is the average and what is the standard deviation. So calculator is an option. Now, for the remainder of class, you guys have a math lab.